In this lecture, we're going to talk about processing of point clouds. A point cloud is given by a set of points, and typically we're dealing with points in 3D space. So all the points together can be encoded as a matrix if we write the XYZ coordinate for each point in a row. So if we look at this matrix P here, then we see that each row is formed by a point. If we have n points, then we have a matrix that has n rows and 3 columns. With Pi, we denote the spatial location of point I, and the spatial location has 3 dimensions. We also have per point features. Per point features can also be encoded in a matrix, and each point I has a corresponding feature vector xi. So the features can change depending on what type of information is available, and we say in this example here that each point feature has d dimensions. So what does a feature vector of a point include? This could be information such as color, normal, curvature, tangent vectors, material properties, and so on. Here we show an example of a point cloud. This is a point cloud of a single object. Similar to image classification, one could ask for the point cloud of a single object. What object does this point cloud depict? Here is a point cloud of a complete scene. A typical question here might be, similar to image segmentation, can we do point cloud segmentation? So, what is the main initial challenge when working with point clouds? Images have a very natural representation as an array or a grid of values. However, points have no natural representation. Maybe one could argue that a natural representation for a point cloud is simply a list of points. What will be possible is that within the list, one point can be close to some of its neighbors, but it's not possible to enforce locality in every sense. It's not possible to order the points in such a way that one point is close to all of its neighbors. Well, maybe we could also order the set of points in a two-dimensional grid of points. Again, that would be possible to some extent, but it is still difficult to maintain the neighborhoods. So it is not really that easy to have an ordering of the points into a grid such that one point is close to all of its spatial neighbors. Finally, we could think about having a set of points inserted into a three-dimensional grid. Here we do have maybe a nice neighborhood in the sense that a point can be close to all of its spatial neighbors. However, having a three-dimensional data structure that is a grid is very memory consuming, and then in sequence there will also be other problems with this might take too much computation and so on. Also, the set of points might be quite sparse, and it is not clear that a sparse grid is always sufficient when dealing with a sparse set of points, because in some areas maybe the points are a lot denser than in others. So there are some ideas how to deal with a set of points and what data structure to use, but there's no obvious answer that doesn't seem to have any drawbacks. To set out and to start with any type of successful processing, the people that looked at this first, or at least had the first major breakthrough, they said, let's start with some neural network that really processes a list of points. In addition, we're not even pretending that we have some good order, we just want the network to actually be permutation invariant. That means that the network should give the same output for every permutation of the input point cloud. Let's say a few things about permutations. Let's say that we have an original point cloud which is given as a list of points x1 to xn. Then a point cloud we ordered by a permutation would look like this, where the first point is now maybe a different index that is determined by the permutation. So in this permutation, 1 maps to a different index pi1 and 2 maps to a different index pi2 and so on. And that means the permutation defines a reordering of the indices. So a permutation can be defined by a bijective function from the index set onto itself. That means the function pi maps any integer in the set 1 to n to another integer in the set 1 to n. We're doing these things a bit slower and in more detail, so the hope is that you can at least understand the original point network PointNet in greater detail, and also this will be part of the project that you implement. So here on top we see an example permutation. The first row of this matrix are the indices simply in sequence 1, 2, 3, 4, 5, and the second row shows what the index on top of it maps to. For example, 1 maps to 3, 2 maps to 5, and 5 maps to 4. So we would write pi of 3 equals 2, or pi of 5 equals 4. The authors of PointNet that set out to introduce this idea of a symmetric function. And a symmetric function is simply a function that is permutation invariant. So for all possible permutations pi, we would like that the function taking in a set of points as input is the same as the function evaluated with the same points but in a different order defined by a permutation pi. To make this simple thing even more obvious, there's this visualization where we have a data structure where each point is shown in a row, and we have n such points, and each point has d dimensions, and then a function that operates on this data structure, this list of points, should give the same output regardless of the order. So for example, on the left, the blue point is in the first row, and on the right, the blue point is in the last row, and on the left, the orange point is in the second row, and on the right, the orange point is in the first row. Examples of symmetric functions are the max, should be a comma, min, sum, average, softmax, product. Of course, there's a design choice in which direction you take the max. So what these functions have to do is they have to be computed per dimension. So for example, let's take this visualization on the right. What we would like to do is, for example, we have the max. We want to compute one maximum value for the first dimension, one maximum for the second dimension, and so on and so forth, until we have one maximum value for the dth dimension. Let's stay very basic. So we have one example point cloud P here, where we have 4 points, where each point is in 3D. So the first point is 1 to 0.3. In this representation, we compute symmetric functions column-wise per dimension. So, for example, if you see some notation in a paper, max P, or max P1, P2, P3, P4, where P1 to P4 are the points, then we would expect a column-wise maximum. So let's go back to our matrix here. So we would go down this column, 1, 1, 0.2, 1.2. So the first value is 1.2. And let's look at the last column, 0.3, 0.5, 1.5, 0.5. So here we have the maximum, 1.5. So the maximum of a set of points has as many components as the points had dimensions. That means the maximum that you compute is independent, or the number of components that you get is independent of the number of points. Therefore, it would be even possible to use this type of networks with a variable number of points. Or at least, if the network is constructed with symmetric functions, then it can be set up in such a way that you can use it with a different number of points. A remark about notation. So the idea is that max h1 to hn, or just max hi, denotes the same thing, maximum computation per dimension. This is another component that we will see used in PointNet shortly, and we would like to discuss it in a bit more detail. The idea is that a multi-layer perceptron, or a fully connected neural network, is applied to a single point. But what does that do? We are dealing with many functions of the form hi of p that map three-dimensional space into R. So in PointNet, we will deal with 1024 of these functions hi. But we would be interested to know, what can one such function express? To visualize that, it's best to think of such function as a scalar field that maps a point to whatever scalar value is there in the corresponding part in space. So what we see is that each of these visualizations is the visualization of one such a function hi, and each of these visualizes a scalar field. So the scalar field is visualized in 3D space inside a box, and we could say, for example, the red region is where the scalar values are a bit higher, the blue region is where the scalar values are lower, and white is where the scalar values are around 0. This is not a perfect visualization of a three-dimensional function because it's hard to make out the differences between the high values and the differences between the low values. But this is only a limitation of the visualization, not a limitation of how these functions actually look like. This is just a simplified visualization, but if you think of what such a function expresses, this function can smoothly vary within the space. So even within the blue regions or the red regions, there would be quite a lot of differences. So one of these functions encodes some spatial information about a point. Maybe is it in the left or right half of space? Is it in one particular corner? Is the point closer to the middle? These type of questions can be answered by one such function. And then, if we now not only have one such function, for example this one shown here, but 1024, we basically evaluate 1024 spatial queries like that in parallel. So this function h down here, h of p, consists of 1024 such individual functions. And this would be the notation. And this is what the MLP can compute for you. So if you see an MLP that is applied pointwise, that means for each point individually, then this MLP has 3 scalars as input and as many scalars as output as you want, 1024 in PointNet. But you should kind of think of each scalar that is computed as basically having being such a scalar function, and the point is used to query this scalar function.